Morning, everybody. More stuff about acyl substitution. Last time, we were talking about reactivity trends. And one of the things that we said was that we have a between group reactivity trend and we have a within group reactivity trend. And the between group reactivity trend, I gave you an order of reactivity. The acyl halides are the most reactive, then the anhydrides, and then the thioesters, and then the esters and the carboxylic acids. They're at about the same level of reactivity. Then the amides and the carboxylates. So that was the between group trend. And then we started to talk a little bit about the within group trend. What if everything that we're trying to assess the reactivity of, what if they're all esters or they're all amides? That between group trend can't help you there. So that's where we left it last time. So let's just briefly recap what we said about the within group trend. The within group acyl reactivity. Okay, so this is just a recap of what we said. All right, and there are a couple of points here. One of them is that big, bulky groups at the carbonyl retard reactivity. So that's nothing new. That's a concept that we talked about when we were talking about the reactivity of aldehydes and ketones. And so if you have a big bulky group near the carbonyl, that's going to slow things down. Another trend that we already talked about before was the electronic trend. And this is more subtle. We have the electronic trend. And this is saying that the best leaving groups are the weakest bases, right? That whole between reactivity trend is based on the quality of the leaving. Cl minus is an excellent leaving because Cl minus is a very weak base. So the acyl chlorides are the most reactive type of acyl derivatives. Amides are very slow to react in acyl substitution because that leaving group is a very powerful base. The best leaving groups are the weakest bases. And so another thing that we have to keep in mind here is that we remember that the weakest bases have the strongest conjugate acids. So when you're looking at that table of pKa's to which we have referred a million times, we know how to use that table and to identify what the strongest acids are. And then we can use this concept here that the strongest acids have the weakest conjugate bases, and that's how we can assess the quality of this, that, or the other leaving group. Okay, so that's a recap of last time. Let's implement these concepts, do some problems. Okay, so let's do a ranking problem. this guy. This one. Oh. Okay, I wrote the same thing twice. What do I need? Oh, I need this. Okay, so these four compounds, let's rank by reactivity, where 1 is equal to the most reactive. Okay, so why don't you study this for a while and let's see what we come up with. Can you spot the winner? Oh, the winner is very easy to identify, I think, anyway. Did you spot the winner? Did you spot who's number 1? Well, this is an amide. This is an amide. This is an amide. This is an ester. So on that reactivity order, we know that esters are more reactive than amides. So any ester is going to be more reactive than any amide. So finding the winner here, oh, that's easy. It's this guy. He's number 1, right? Because esters are more reactive than amides. So there we're using our between group trend. Okay, but now all of the rest of these are all amides. That between group trend can't help us now. So who is going to be the loser here? Did you spot the loser? Who's number 4? He's pretty easy to spot. Okay, amide, amide, amide. Big fishtail here. That's much. Big fishtail here. That's a big bulky group at the carbonyl. No fishtail here. Right, so we're looking at how these two guys down here on the bottom, they have a big bulky group at the carbonyl. That's going to slow down the reactivity. Another thing I see is this trifluoromethyl group that is present here and here. What about this trifluoromethyl group? Is it speeding things up or is it slowing things down? Well, the fluorine is highly electronegative. It's an electron withdrawing group. And we know from way long time ago when we were talking about acids and bases, is that electron withdrawing groups increase acidity. If something is increasing acidity, what is it doing to basicity? It is weakening basicity. So that something that has that trifluoromethyl group is going to be more reactive in acyl substitution than something that lacks it. Okay, so we're ready to rank. This guy's the loser. Why? Big, bulky fishtail at the carbonyl and no electron withdrawing group that is decreasing basicity. And remember, the best leaving groups are the weakest bases. So this guy, he's the loser. Between this guy and this guy, we see they both have that trifluoromethyl phenyl substituent. That's going to be the leaving group. The leaving group, this bond here between the carbonyl carbon and the thing that's not carbon, not hydrogen, that's going to break off. This guy has a fishtail. This one doesn't. The leaving group is the same. So that this is going to be number 3, and this is going to be number 2. Okay, so that would be the order of reactivity here. So, is that making sense? Okay, let's try another one. Okay, so once again, rank by reactivity in acyl substitution. 1 is the most reactive. Okay, so let's look at this. Look at these 4 molecules and see what we come up with. To spot the winner, oh, that's so easy. Who's the winner? This guy's an ester. This guy's an ester. This guy's an ester. But this is an acyl chloride. And they're at the top of the heap. They're the most reactive acyl derivatives. So the rest of the decoration around this molecule doesn't really matter. I mean, that's a big bulky substituent. Don't matter. Acyl halides are much more reactive than the esters. So that's going to be number 1. Okay, so now that's the between group trend. That doesn't help us anymore because that's an ester, that's an ester, that's an ester. Okay, and so I see on the left-hand side of the carbonyl a tiny, teeny, tiny hydrogen, teeny, tiny hydrogen, teeny, tiny hydrogen. So we're not looking for any insight about reactivity on the left-hand side of the carbonyl. Now we have to look at the right-hand side. And once again, big, bulky substituents at the carbonyl are going to slow things down. Fishtail, this is much bulkier than this because this fishtail points up and down. It's just a much bulkier substituent than something that is more or less straight chain like that. Okay, so and I see the nitro group. That's an electron withdrawing group. What's an electron withdrawing group? Due to acidity, increases acidity. What does an electron withdrawing group do to basicity? Decrease basicity. So that this thing with the nitro substituent, that is going to be the weakest base leaving group of what is left. So that is going to be number 2. This is going to be number 3. This guy, number 3, looks just like number 2, except it is lacking that electron withdrawing nitro group that is speeding up the acyl substitution. And this guy, no electron withdrawing group, big bulky substituent over here in the leaving group. So this is going to be number 4. Okay, so that would be our ranking of reactivity for an acyl substitution. Okay, so now let's talk about the big payoff about reactivity is leading up to this moment, which are the consequences of the reactivity order. All right, and this concept can pretty much be distilled down to one sentence, and that is, you can make a less reactive AC from a more reactive AC, comma, but not a more reactive acyl from a less reactive AC. Another way of saying the same concept is that you can go down the reactivity ladder, but you can't go up the reactivity ladder. So, show you some examples here. All right, so I want to have say if I start out with this acyl halide, these are the most reactive types of acyl derivatives. They're way at the top, and I react this with alcohol under acidic conditions. So there's the carbonyl-carbon bonded to something that's not carbon, not hydrogen. This thing that's not carbon, not hydrogen, that's going to take off. The nucleophile minus a proton on the nucleophilic atom is going to take its place. And so we get an ester plus HCl. Okay, so here we're going down the reactivity ladder. We're going from an acyl halide, which is way up here, to an ester, which is near the bottom of the reactivity scale. So that's a big check, yes. Okay, but now contrast that with this. Start out with an ester. Add HCl. Do we need acid when we're using HCl? No, because HCl has the acid built in, so we're not writing H plus above the arrow. We don't need any acid. And so there's the carbonyl-carbon that's bonded to something that's not carbon, not hydrogen. This thing is going to break off the nucleophile, which is Cl minus, minus the proton on the nucleophilic atom. It's going to take its place. And so maybe we're tempted to write something like this, but this is a total no-go. This would never happen because we're going from a less reactive acyl derivative to a more reactive acyl derivative. So when you mix this and this together, what happens? This, no. What happens? No reaction. RXN means reaction, no reaction. So you're mixing these two together, you're not going to get this. Nothing's going to happen because you're going up the reactivity ladder, and that is not allowed. So this is the big consequence of acyl substitution reactivity, is that just because we can write a reaction on a piece of paper doesn't mean it has any basis in reality. So this reaction here, this is like a unicorn. This is a total fantasy. It's up there with the Easter Bunny as far as reality is concerned. Okay, so let's explain why this is and try to understand this reactivity order. Okay, so let's look at another fantastical reaction that would never happen. Let's say maybe I have an ester, and I'm going to react that with a thiol. Acidic conditions. So what's supposed to happen here is that the thing that's not carbon, not hydrogen, is supposed to break off from the acyl carbonyl. The nucleophile, which would be sulfur here, is going to take the place of the departing leaving group minus the proton on the nucleophilic atom. So if we just mechanically, sort of without thinking, if we just mechanically write the acyl substitution, now look at the products. We've made a thioester. Thioester is quite reactive. Look at that list of between group reactivities that I gave you. The thioester is pretty reactive, and it has been created in the presence of a nucleophile. Oxygen, this is a nucleophilic atom. This has a proton on it. We're still under acidic conditions. The acid is a catalyst. So the minute, the instant that this molecule is created, it's going to back react with this nucleophile. This is a recipe for acyl substitution. It has a carbonyl-carbon bonded to something that's not carbon, not hydrogen. This is going to break off. The nucleophile minus the proton is going to take its place. And so if these two guys are ever in the same company, what they're going to do is an acyl substitution reaction. And where is this going to lead us? Right back to starting material. So we're mixing this and this together in the laboratory, and nothing is happening because something is happening at the microscopic level. This reaction is happening at a microscopic level, but when these two molecules find themselves in each other's company, they immediately back react to form starting material. Because the thioester is pretty darn reactive. So once again, this is an example of this plus this. What's the correct answer? No reaction. Absolutely nothing will happen. Even though I can write it on a piece of paper, my blackboard didn't catch fire or blow up or anything like that. But this is a total fantasy here. This is up there with Santa Claus and the Tooth Fairy and Bigfoot. You know, it's just total fantasy, would never, ever happen. All right, so
on a test, if you were to ask like put that and say like product prediction,
yeah,
would you want
the correct answer is no reaction.
Okay, thank you.
Okay, so now the truth is so messy, right? Because I've just given you a fundamental principle of acyl substitution. The truth, however, is so messy. There are exceptions to this fact that you can go down the ladder, but you can't go up the reactivity ladder. Unfortunately, there are some exceptions, and there are pretty important. Okay, exception number one. The amide, if you've taken amide, react that with water, and under acidic or basic conditions, H plus or OH minus, you can get this reaction to go. There's the carbonyl-carbon bonded to something that's not carbon, not hydrogen. I'm just going to put an R here. It's weird. There's the carbonyl-carbon bonded to something that's not carbon, not hydrogen. The thing that's not carbon, not hydrogen is going to break off. The nucleophile minus the proton and the nucleophilic atom will take its place. And so if I just mechanically implement the basic recipe of acyl substitution, that's what I get. But hold on. I'm going from an amide to a carboxylic acid. This is uphill, but this will work. This is an important exception, is that an amide plus water, acid or base, yep, you can go up the reactivity ladder. But this takes very harsh conditions. If I'm doing this in acid, this is going to be 6 molar HCl and boil for about 6 hours. Very strenuous, very tough conditions. If I do it in base, I would need something like 40% potassium hydroxide, and once again, boil for about 3 or 4 hours. Very, very tough reaction, but it will work. The amide is a very rugged functional group. It requires this forcing conditions for the amide to do anything. And let us thank heaven for small blessings, because proteins, that's what all of your soft tissues are made out of. Your hair, your skin, all of your internal organs, they're all made out of proteins. Proteins are polyamides. The amide is a very, very rugged functional group. You're about 85% water. Why aren't you sitting there being a big puddle? The reason is because there's a lot of water inside your body, but most of your most of your structure that isn't bone is made out of amides, polyamides called proteins, and these are very rugged functional groups. They only fall apart under very forcing conditions. So that's the most important exception to the reactivity ladder. And it's a very important one because, you know, at lunch today, when you eat that hamburger or eat that tofu, you're eating protein. The HCl in your stomach is reacting with the 85% of you, which is water. And that protein, that amide, that polyamide is going to be torn down. That cow protein, that soybean protein is going to be torn down into carboxylic acids, and then it's going to be built back up into a human being protein. Okay, but so now, so that's a very important exception to this reactivity ladder. Okay, but now let's look at this. There's the same amide, and you know how water is HO, H-O-H, you know how water is HO? Now what I'm going to do, instead of H-O-H, I'm going to replace the second H of water with CH3. So this is an amide plus an alcohol, acidic conditions or basic conditions, no reaction. Right? Because now I'm going up the reactivity ladder from an amide to an ester, and that is not allowed. The only acyl substitution that an amide ever does is reaction with water. Amides don't react with alcohols. They don't react with any other kind of nucleophile here. This is the one and only exception to that reactivity ladder dealing with the amides. Okay, so that's a very important exception. Let's talk about more exceptions. Okay, exception number 2 would be the kind of looks like an acyl substitution reaction, but it isn't. So it's not really an exception, but better talk about it anyway. There's the carboxylate on that order of reactivity. This was the cellar dweller, way at the bottom. This is the least reactive acyl derivative. Well, that makes total sense. Because what happens in acyl substitution is the nucleophile attacks the acyl carbon. The nucleophile is something that's electron rich. Electrons are negative. The nucleophile is negative. A negative thing, a negative chemical species, is not going to want to get anywhere close to something that has a negative charge on it. So it makes total sense that the carboxylate, this guy, is the very least reactive acyl derivative. But when I take this guy and react him with HCl, what's going to happen here? Can you guess? Is the O minus going to break off and the Cl take its place? Is it going to be an acyl substitution? No, it is not, because that's a base. That's an acid. We get an acid-base reaction, not an acyl substitution reaction, an acid-base reaction. And so that O minus gets the proton and it robs it from the HCl. And so if you just look at that reactivity ladder, it looks like we moved up the reactivity ladder. It looks like we went from a carboxylate, which is way the hell down here, to a carboxylic acid. It looks like we moved up the reactivity ladder. We did, but this is not an acyl substitution. This is an acid-base reaction, right? So it kind of looks like it would be an exception that you're moving up the ladder, but you're really not. Well, you are in a way, but you're not moving up the ladder by an acyl substitution. Okay, So that's something else that can happen that looks like an exception, but it really isn't. Okay, let's talk about another exception. And this is that carboxylic acids and esters are very closely matched in reactivity, so that these two groups freely interconvert. So they're about the same level of reactivity. They can interconvert one from the other, but only in acid. So I could take a carboxylic acid, react that with an alcohol, add acid. I'm going to get an acyl substitution reaction. The nucleophile came in, kicked out the leaving group. Okay, that's going to work. That's okay. I could also take an ester, react it with water and acid, and I can go back to the starting material. So I could take an ester, something like this, react that with water, add acid, go back to a carboxylic acid plus the lead. So esters and carboxylic acids, although they don't exactly have the same reactivity, they are freely interconverted in acid only. So that's a check. Okay, but an acid and an ester are not interconverted in base. So this is okay, but let me show you what is not okay. But if I start out with an acid, right, and now I'm going to try acyl substitution basic conditions. So that means instead of HOCH3 and acid, I need the basic counterpart, O minus CH3. And HOCH3 as the solvent. Right, so that's the nucleophile, but this is a solvent. Notice how they match. Okay, so I might be tempted to think, oh, well, that's the carbonyl carbon. That's the thing that's not carbon, not hydrogen. This is going to break off. The nucleophile is going to take its place. These are basic conditions. That's why there aren't any protons around. But that would be wrong. What is going to happen here is just an acid-base reaction, right? It's not acyl substitution. The pKa of a carboxylic acid is 5. The pKa of an alcohol is 17. The equilibrium constant using that Henderson-Hasselbalch equation is 10 to the 12th. That's a huge equilibrium constant that favors this acid-base reaction. So it looks like I moved down the reactivity ladder from a carboxylic acid to a carboxylate, but I didn't do that by acyl substitution. Once again, it's an acid-base reaction. So that, just to repeat, is that acids, carboxylic acids and esters freely interconvert in acid conditions, but they do not interconvert under basic conditions. You're just going to get this acyl substitution. You're just going to get this acid-base reaction. Okay. All right, next exception, I guess this is exception number 4, which is that if you're staying within the same group, pretty much you can convert one ester to another ester. You can convert one amide to another amide. You don't have to go down the reactivity ladder. If you're staying at the same level, that's also okay. So something like this, if you start out with this ester, react it with this alcohol, acidic conditions, the carbonyl, the thing that's bonded to the carbonyl carbon is going to break off. The nucleophile minus the proton will take its place. This is okay. See, we're not moving down the ladder. We're staying at the same level. An ester, a new ester is being created from a pre-existing ester. That's okay. So we have that all-important reactivity ladder, but we see that there's some things that we can do and things that we cannot do in the context of that reactivity ladder. Okay. So let's talk about an application of acyl substitution. I think maybe we'll talk about acyl substitution today and maybe a little bit on Wednesday, and then it's time to move on to our next family of reactions. Let's talk about polymers. All right, so polymers, these are materials that are just ubiquitous. We see them everywhere. They're fixtures of daily life. Most of the clothes, a lot of the clothes that you're wearing, you know, unless it's some kind of luxurious natural material like cotton or wool or something like that, it's probably a synthetic polymer. Cotton and wool happen to be polymers also. Cotton is a polymer of cellulose. It's a poly, sort of like a polysaccharide. Wool is a protein. That protein is an amide polymer. But those aren't the kinds of polymers I'm talking about. Now I'm talking about these synthetic polymers. Okay, so let me set up the situation for you. Let's say you have so there's an ester, and I'm going to react that with this guy. And acidic conditions. Okay, carbonyl carbon bonded to something that's not carbon, not hydrogen. This OCH3 is going to break off. The nucleophile is this nitrogen atom. It's going to come in minus a proton. So I'm going to do that to one end here. It's going to be a lot of writing here. Okay, so we see that we went from an ester to an amide, and that's okay because we're going down the reactivity ladder. Okay, so far so good. Now, what if we were to add more of this guy to this? So let's add another molecule of this diester here. And acidic conditions. Well, now this nitrogen here, this has a free nitrogen atom, This is a carbonyl carbon bonded to something that's not carbon, not hydrogen. This can break off, and this can take off. And so we'll get that was the nucleophile. That nitrogen atom was the nucleophile. It attacked this acyl carbon. This CH3O went away. Okay, and so now we have that. Okay, and now let's imagine we add more of this guy. And a little bit more acid. And we see we can have another acyl substitution reaction. There's the nucleophile with the proton. And here's the carbonyl carbon that's bonded to something that's not carbon, not hydrogen. This is going to break off, and the nucleophile is going to take its place. So once again, we would get a lot of writing. We would get that. And once again, we've gone from an ester to an amide, and that's okay. And now what if I were to take this guy again? Etc. And so we see that we have what is happening here is that we're creating a chain, creating this chain where we're getting one acyl substitution after the other, and it's all building up on the end of this chain. This is a polymer, right? And we could just keep going. In the laboratory, making this kind of polymer is actually quite easy. You just mix this plus this, some acid, melt them all together, and under controlled conditions, this polymer happens. Okay, the polymer has a repeating unit in it, and that repeating unit is usually enclosed in brackets. So let's see what the repeating unit is here. You can start the examination of the repeating unit anywhere you want. I'm going to start it here, right? I'm going to put my little bracket there. And now I'm going to munch my way down this chain and see where does this repeater start over. Carbonyl, NH, benzene, NH, carbonyl still hasn't repeated yet. Oh, but now I see that carbonyl, benzene, carbonyl. Oh, okay, there's the, whoops. There's the end of the repeating unit, right? Carbonyl, NH, benzene, NH, carbonyl, benzene. Did you get all that? Carbonyl, NH, benzene, da 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 da. It would just keep going. So this is the repeating unit of the polymer, and depending on how many repeating units we have, usually write a little N here or an X or something like that to show that this could be 10, hundreds, thousands, even maybe sometimes millions. All right, so this is how many polymers are made. This polymer is an interesting polymer. It's Kevlar, right? This guy here. This is the synthesis of Kevlar. Any ever heard of Kevlar? Do you know what Kevlar is used for? Anybody out there know? Ever heard of Kevlar? Bulletproof vests. That's one of the applications of this polymer. So that this, this would be the synthesis of how that material could be made. Okay, so this is pretty hard, right? Visualizing these stepwise reactions. And also, it's pretty difficult to identify this repeating unit. So let's do some more practice. Okay, so what about if we were to take this guy and react him with this? Throw in some acid, heat, you get a polymer. So draw the structure of the polymer. I'm particularly interested in looking at its repeating unit. Okay, so there's the carbonyl carbon bonded to something that's not carbon, not hydrogen. This is going to break off. That's the nucleophile. It's going to take its place. So just right now, when you're a beginner thinking about polymers, maybe the best thing would be to draw each of the steps until you can confidently identify the repeating unit. Okay, so the first two molecules got together. I went from an ester to another ester. That's okay. I'm at the same reactivity level. But now this is a nucleophilic atom. It has that proton on there, and it's in the company of 10 to the 23rd other molecules like this, right? I'm not mixing one molecule of this and one molecule of this. That never happens in the laboratory. You're mixing 10 to the 23rd of these with 10 to the 23rd of these. So you have lots and lots of this diester that hasn't done anything yet. So this nucleophile is going to attack another acyl carbonyl and kick out the leaving. Okay, so there we had another acyl substitution where I kicked off this leaving group and the nucleophile went in. Okay, and now that's an acyl carbonyl. That's an acyl carbonyl. Now I can have another acyl substitution reaction on the other side. Where another molecule of nucleophile came in. So notice it's electrophile plus nucleophile, and now another nucleophile came in, and now this is another nucleophilic atom. It has a proton on it, and we have more of these available, so we could have yet another acyl substitution where the end of this chain just keeps getting bigger and bigger and bigger and bigger as a result of all of these successive acyl substitutions. Okay, so this will be the last one. We could go on, but we won't. Just repeating, just redrawing everything. This oxygen atom did an acyl substitution on another molecule of diester, and we got that. And then we could keep going on and on and on and on. And this chain could get bigger and bigger and bigger, 10, 100,000, sometimes even millions of units, depending on what it is you want to make. Okay, so now let's identify the repeater. So just start anywhere and try to identify where that repeater begins to repeat. Okay, so I'm going to start maybe here, and I'm going to munch my way down the chain and see where this comes back up again. Oxygen, CH2, 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 oxygen, carbonyl, CH2, carbonyl, oxygen, CH2. Okay, so this part of the molecule is now repeating something that I saw earlier, so I'm going to close it off here. So this guy would be here, and then if I kept going, this repeater would be replicated over and over and over and over again. So that's my repeating unit in this polymer. This guy is a polyester. I personally never touch the stuff, but maybe a lot of clothing is made out of polyester. Maybe you've heard of that. This is a polyester. Okay, so let's try this game in reverse. Okay, so I'm going to try to show you some pretty pictures of polymers now. Okay, so see this lady? Yeah, Dacron. She's maybe allergic to or can't afford down. So she has to use this synthetic polymer, Dacron. Okay, so if you want to be good, if you want to take notes, if you want to play along, copy down the structure of Dacron and tell me how is it made. There's the repeating unit. I've enclosed the repeater in brackets, and I put a little N to show that that is what's repeated over and over and over again. Give me the recipe for Dacron. How would you make this polymer? Okay, I will be good also, and I will copy this down. Okay, so there's the Dacron repeating unit. I see that's a carbonyl carbon. It's bonded to something that is not carbon, not hydrogen. And so this oxygen had to come from the nucleophile. And this nucleophilic oxygen came in here and kicked something out. So how would I make Dacron? The recipe would be, I take this alcohol, and I'm going to react that with an acyl derivative that has something here, but I have to make sure that I'm going down the reactivity ladder or staying at the same level. So a very good choice here would be to put a Cl, right? That's the top of the reactivity ladder. A very good choice would be Cl there as well. So I would need acid conditions. I would probably have to melt these two together. And so that would be the recipe for this Dacron using that successive acyl substitution reaction. And so I hope that you could see where I'm coming up with this recipe by looking at the repeater, right? The all-important acyl carbonyl, this guy right here. There used to be something on there that got kicked off by the nucleophile, which was this. There used to be something up here that got kicked off by the nucleophile, right? And who lives there? Well, this oxygen does, because that's the repeater. This just keeps extending on and on and on. Okay, so tomorrow maybe we'll wrap up more stuff about polymers and then move on to amino acids. So any questions about anything before we sign off? Okay, see you next time. Oh. No, pre-lab's over. Okay. Anybody else? Okay, bye-bye.